right, so we revisit our universal Turing machines, right? So what was the universal Turing machine? We do a very slight modification now. A Turing machine U was a universal Turing machine, right? So it simulates other Turing machines. Now, for all strings U, you have a string U and an input V. But before, we would only allow input V to contain zeros and ones. What I do now is I allow it to also contain hashtags. So you have a string U and an input that contains zeros, ones, and hashtags. So instead of just containing zeros and one, then machine U started with U hashtag V, so the universal machine, that's the definition. If you start it on U hashtag V, it will simulate MU on input V. So it basically looks for the first hashtag, and then whatever is written before the first hashtag is taken as a machine. So it simulates MU on input V, but now input V might also contain hashtags. So I'm allowing this to happen because I need it. And then we did if you remember, we did the coding of the machine. So now I have to change the coding because I have an accept and reject states also. So first of all, this is what I do. So I have a Turing machine MZA delta Z0 accept states and reject states. This is my new machine now, which is equivalent. And what I do, I number the states as I did before. So my states are Z0 to ZR and my letters are A1 to AS. So I give them each natural numbers from 0 to R for states, from 1 to S for alphabet symbols. And I take Z0 as my start state. So my start state is always numbered Z0. And what I do is my end state, so I have accepting states and reject states, right? So I assume that, first of all, I assume that I only have one accept state and one reject state. Why can I do this? Why can I always assume that I have just one accept state and one reject state instead of 10 accept states and 15 reject states? And you will do the same with reject state, right? You will just send all of them into one and just call that one the reject state. So I can, without loss of generality, I can assume that I have one accept state and one reject state. So I will also always do this. And in the numbering, I will assume that accepting state is the one before the last one, and the reject state is the last state. So ZR will be reject state, and ZR minus one will, so one before the last one will always be an accept state. All right, now I want to turn my Turing machines into numbers again, into strings. So you're familiar with this, right? So every software is basically a string. So this is the same thing with Turing machines. Turing machines are just codes, so codes are strings. So what I do is additionally to simplify my computation, I want all of the strings to have the same size, basically. So not strings, so you'll see in a moment. So here, so let's say now, as I did before, let's enlarge this part. Let's say, so if I'm in state Zi, so I have a number assigned, and in letter Aj, from state Zi, I read letter Aj, I have to go to state Zk, overwrite letter Al, and make a movement M, so which is M is left, neutral, or right. So I want to code this now. What I do is I code it this way. I put hashtag, and then I put a binary representation of I, so this is maybe 17, some number, so I put 17 in binary, but this F here means that this F is just, I fill this binary representations with zeros somehow. So what I do really want to do, so let's say, show you an example, maybe it's the best description. Let's say I have to code state Z2. So this is, in binary, this codes as 1, 0. But if I, let's say, I also have state, let's say, Z, so my largest state, let's say, so let's say my letters, I only have just 2 letters, 0 and 1, and I have states, my states are Z0 up to what? Z7 or whatever. Or maybe even Z8, let's make it Z8 so it's easy. Then Z8 in binary will be what? So it's 1, 0, 0, 0 or something, right? So in binary it is like this, but this has size 4, right? So this has size 4. So what I want to do, instead of writing it this way, I want to all of them to have size 4. So I take like 0, 0, 1, 0. Okay? So what I will do is I will find the maximum number that I have to code. So this will be a number of states plus 1, a maximum number from however many states I have plus 1, or however many letters I have plus 1. So I take the maximum number that I will need to ever code, and I take the log of that. That would be the size of this thing in binary. Okay? So size of this thing in binary is basically log of this, rounded up, right? So I take this to be f, and I make it so that all my codes are of size f. And if it's shorter, I fill it with zeros. So yeah, this is exactly what this f's here stands for. So log meaning you take the length of this thing in binary, and then you code these things here, and in the end, yeah, I haven't yet emphasized this. So your code is this so you code I in binary, but you make it of length f. You code j in binary, make it length f, you k, l. So this basically tells you that in state zi, if you read aj, you go to state zk, you overwrite letter al, and you make movement m prime, and m prime you want a binary, so you put 0, 0 if it's left, 0, 1 stands for neutral, and 1, 0 stands for right. Okay, so now this thing is like binary things. All of them are length f other than m. So these are m is length 2, so length f, 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 f. So this will be 1, 2, 3, 4, 5 times length f, or 4 times length f plus 2. And then you have additional hashtags. So codes of states and letters all have length f. Okay, now I want to also get rid of my hashtags. And this is the same trick I did before. So this code I call code prime because I still have to do one more operation. Code prime, and you just concatenate all such strings together and then put symbol hashtag in front. Now all words can be found by searching for 2 hashtags. Because if you concatenate all i's like this, you concatenate all deltas, if you see 2 hashtags, you know that you're changing to a different delta. So now you can, by finding 2 hashtags, you can locate each transition function basically. And now you change it, so now I want to turn it to completely binary, so I change the code, and I call this code H. We'll go get back to this guy when we do complexity. I change 0 to 0, 0, I change 1 to 0, 1, and I change hashtag to 1, 0. So the only place you will see 1, 0 now, if you read by 2's, it will be hashtag. So you're able to recognize hashtags now. And again, we do the same thing. It's just a slight modification. MU, what is MU? It's a machine M which has code U. So U is now this code here, just a string. If it exists, and if it doesn't exist, I mean, if you give me a code that corresponds to a no program or no machine, then I will say that MU is just a trivial machine. So it just halts and does nothing. So now every string has a machine. You just have to decode it and you get the... And we already proved such thing. Oh, we have not proved this. We have to prove it now. We prove something like that. There's a universal one-tape Turing machine U, which simulates t steps of mu started with input v of length v equals n in time O u times n squared plus u squared times t. So if mu uses space s, then u uses space OUS. I just realized now that when we proved this, I don't remember, I thought we did this, but when we proved the simulation of when we get from k tapes to one tape Turing machine, did we prove this complexity things? Did we prove the bounds for I don't remember if we proved the bounds for time and space there. I think we did. Okay, anyway, so here it's different that so now we want to prove how much does this simulate. Let me actually see if we did this. So I don't remember if we actually proved the time, but since we redefined our universal Turing machine anyway, so let's look at the proof and let's remember the proof if we did this. I don't recall. Yeah. So how do we do this, right? So again, we split our thing in tracks. So I will have track 1, track 2, track 3, and track 4. This is just one large tape, but it's split in 4 tracks. So this machine is supposed to simulate the other machine acting on an input, right? So on track 1, right? So let's say I have a K-tape Turing machine M. So I have a K-tape Turing machine M. That means so it's a configuration K of one tape Turing machine M, right? So what is a configuration? So you have something written here. You're in some state Zj, and you're reading something, right? This is just written a configuration, and I want to simulate this configuration here on my K tracks. So on track 1, I will encode the tape of mu in the obvious way. So let me write down so let me get my pen. So I want to simulate mu acting on V. This is what I want to simulate now with my machine. And what I know is I know the code of U. So I have to unpack my code and do the movements according to how U would act. So I want to simulate this on my machine U. So I'm describing you the machine U. So machine U has one tape, but it has 4 tracks, right? On track 1, I encode the tape mu in the obvious way. So basically, let's draw this way. So I have something like this. Then I have 4 tracks. So I have 4 tracks. However, this is just one cell. So on track, and then let's just mark some place where we will start. So that let's mark this place. So here I would write binary of ix, where ix is just the configuration here. So ix just is a number, maybe like ix is 7, for example, and that means that I'm coding a 7 here, basically. So I have on the first track, I code wherever the head, so here is wherever head is standing, I'm coding that letter here, and here I will code binary, so there will be a hashtag then. So I code it in this way. So I put hashtag here, there's another track, and then here I will put binary of ix minus 1 and so on. And here I will have, like, I don't know, hashtag, and then I will have, say, binary ix plus 1, right? So I'm coding the input of the machine on the first track. On the second track, I'm coding the state. So here I would write binary j, meaning I'm in state zj. See, I'm in state zj and I'm looking at aix, so I code this here and then I put blanks everywhere else. That's where I mark this spot, right? And here now, starting exactly at this spot, I will write h minus 1 u. What is this? So I have to unpack the whole code u. So h is what? H is exactly coding this thing here, and h minus 1 basically returns code prime of m. So here I just write the code of my machine, m prime, which will be like zeros, ones, and hashtags. So here maybe it's like 0, 1, hashtag, 1, 0, blah, blah, blah. All transition functions of my machine that I'm supposed to simulate are written up here on track 3. And on track 4, I do computations, basically. So track 2 codes the state m in obvious way. Track 3 codes code prime of mu. Code prime is different from code that it also contains hashtags, starting at the head position of mu, like this. And track 4 is used for simulating steps. So more tracks are possible for the comfort of your programming, for example. So how would I simulate now? How would I simulate a step? So this is the same picture, by the way. So first of all, I also have to track how many steps I'm doing. Now, this is where this F will come in. On track 3, imagine now, on track 3, I have code of U completely written out like this, with hashtags in the middle, right? On track 3. And so it's basically h minus 1u. So u is just a binary string. H minus 1u is a string, actually the code of mu with hashtags. And what I have to do is to actually do this unpacking. I have to remove doubles. I have to change 00 to 0, 01 to 1, and 10 to hashtag. So what I'm doing, let me just, so if I have a code like this, let's say 00, 01, 00, 01, and 10, I have to, I'm changing what I'm writing on track 3, I have to change it to 01 hashtag. Because this is what I did when I went from hashtags. I doubled everything, and what I did is, did I do 101? Let me just check. Yes, this is correct. So for 0, I put 00. For 1, I put 01. And for hashtag, I put 10. So I have to go back now. I have to write this thing here. So now my question is, how many steps does this thing need? Let me pause this and you answer the question. Actually, so why are we doing this? Why are we writing in hashtags? So what you really want, you need something like this to read it. Somehow your machine has to read what is happening. As an input, it gets just a binary string. So it gets... So I only have one tape. On the first track, I have so I'm supposed to simulate M on input V. Look what's happening. I'm simulating M on input V. To simulate M on input V, I have to know what M is, what V is, right? So first, on the first track, I write V in the beginning. So I put the input of my machine that I'm trying to simulate. On the second track, I'm keeping a track where the head of M is moving. On the third track, I have to record, I have to somehow remember what are the transition functions of M. And what I'm getting passed on is just the string U, and I have to unpack the transition functions. They give me the code of U in doubling times. So I have to unpack the transition function, and in order to unpack, I have to reverse this process of doubling. So exactly, so what I'm doing here is pre-processing. So on track 3, first I have to remove the extra zeros and extra zeros and change 10 to hashtag. Every removal creates so if I remove 10 from 00, it creates a gap. So erasing the gap, meaning shifting everything. So you have to erase, create a gap, shift. Erase, create a gap, shift. Again, erase 10, write a hashtag, but this creates one gap. So you have to go back and shift everything by 1. So this shifting back and forth, if the whole length of the thing is U squared. So plus some or times some constant. So this takes OU squared amount of time. I don't think we proved this. Maybe we just said this last time, and I actually used this proof in the previous lectures, saying as if we proved it, but anyways, we prove it now. Then, what I have to do, I have to expand symbols 01 and hashtag in input V to do length F and separate by symbols hashtag. So now, after I remove these things and I expand it, I have to, so if I had something like this, 10, and if my F was 4, if you remember, I have to add 2 zeros here. So now I have to expand everything up to F. So what I do is, this expansion, now imagine if I'm doing, so let me ask you this question then, and you answer why. So let's actually explain it one more time. So the length of the whole thing is n times f, because there are n entries in there and you are making each one length f. So the whole length is f, so it's in proportion to f times n, and every time you add on stuff, so if you're expanding one place up to f, you have to shift everything to the right and also shift everything. So maybe you're expanding it up to F, so you're shifting everything to the right. You're expanding the other guy, shifting everything, expanding and shifting. The shifting blows up in quadratic time. So it's F times n squared. And since I know that length of U is bigger than F, F is just the logarithm of something, so it's quite small, but U is the code of whole thing. So I will just write, instead of F times n squared, I will write time U times n squared. Because I already used U squared here, so might as well just take U squared here, because it will be less than this if I put F. So it will be, I take U times n squared, and the space that I need, it's F times n. So if I expand n times n entries up to F, the space I need is F times n. So the space will be, again, I substitute U for F, and I take U times n. And then what I do is I have to just move code down exactly. So I have to move code of MU, which is on track 3 here, the actual explanation of U, under the encryption of track 1. So I have to then shift the whole thing under so that it exactly is aligned at where the state sits. So I do this, and again it takes us U squared times because you're shifting everything. So moving the encryption takes, so you shift 1, shift 2, shift, then you go back, shift 1 more guy. So shifting always takes the square amount of time. So we saw this already, and so let's not. So now everything is set up. Now you only have to simulate what? How do you simulate now? Think about it. Let's think how you simulate. I'm in state J and I'm reading IX. What I will do now, let me just show you. So I know that the letter that I'm looking at is IX, so this is the situation. And I'm in state J. How do I simulate what to do? So what I do is I look here on track 3, I start searching. As soon as I see binary J and IX, look, so how does my coding work? So as soon as I will see I and J, I will have to go to state K, overwrite L, and do M. So I'm just searching. So what this machine is basically doing is it's actually, if it sees I here and J here, it searches for IJ here, and as soon as it finds state I reading J, it will just look what is next. Let's say state K. Then it has to change this track to state K. If it's letter AL, then it has to erase letter AL, and then it sees the movement. Let's say it's 1, 0, means it has to go left. Then it has to shift everything to the left. So it's basically read this, search in the code for what should I do, and then do what you're supposed to do. Track number 4 is maybe you have to save something, and for computations and this. For comfort of programming, so you use it because you never touch these tracks. Basically, all the computation are happening on track 4. So when I say you have to search, what does it mean you have to search? Maybe you have to write down something in track 4 and then look for it, and so on and so on. So it's like used for computations. But input. So what happens in the beginning? That's actually a good question. In the beginning, on track 1, you have the input V, written in binary, whatever, encoded in binary. On track 2, you have the start state of the machine you're simulating. On track 3, you have the whole code of your machine you're simulating, meaning you know what to do when, right? So what is the first step you do? So in the first step, on track 3, you're looking for the start state. So you're looking for the start state such that after start state, you have the symbol you're looking at. So V1. So you're looking start state V1, what to do? You have to go to state 14, let's say, and overwrite V17. Then what you do is you change this to state 14, you change this to V17, whatever is on track 1, you change track 1 to V17, you change track 2 to Z14, and then you have to shift everything according to what you're doing. So if you're going left, you have to shift everything left. If you're going right, you have to shift everything right. This is basically, and you're doing it over and over again. This is what is written here. Produce, yeah, this is what track 4 is used for example. This is actually searching what I said. How do you search for something? So you want to find state J and I. That's reading I. So on track 4, you write hashtag JI. See, so you're searching for state J followed by I. So how do you search? You write it on track 4. Then search for this pattern exactly on track 3. So I'm searching on track 3 a pattern that exactly begins like this. If it is not found, by the way, if you never find this pattern, that means you are in the end state. Because for end states, you do not have transition functions. So these things are not written for end states, because you do not have transition functions for end. You halt in end states. So if your search goes to the end so that you never find it, you say that, then you're in the end state. So your end state, if it's r-1, so if your J here, the state is r-1, I know that r- was an accepting state. I said this here. I said that r-1 is an accepting, and I accept. If it's not r-1, then I reject. Now, if I find something and it's followed by fk, fl, unless the computation is, you override track 4 by it and move this back to the head position, exactly as I explained. You override on track 2 the state, and you override symbol on track 1 with L, and dependent on the move encryption, track 2 and track 3, you move it by f+1 many symbols. This is where f is important. Let me explain this in Georgian. So depending on M, you have to move the encryption, and this is where exactly f is important, because if you do not know the length, you do not know. So let's say if you're encoding letter number 2, let's say, then it's 1 0, and you just have to shift by just 2 things. But if you're encoding let's say state number 4, it's 1 0 0, and you have to shift by 3 things. So which one do you do? What you do is you fill all of them to length f, and you're always guaranteed that if you shift by f+1, because 1 is for the hashtag here, so if you shift by f+1, somehow you're guaranteed that you will always end up on the encryption of the next letter. This is why we did it for f's. And by the way, so simulation of the step takes OU² amount of time. Again, so it doesn't, this is actually an exercise, you can think about it. If the tape encryption of MU has length S, then the encryption of track 1 of U has length F times S. So if encryption had length S, then it's, of course, you increased each one of them by F. So if S+1 times F plus, and hashtags for F+1, and it's U times S. So in the end, this pre-processing that we described, this U² takes the cake, and so the simulation takes square amount of time of size of U, and it takes space, the linear space. So the simulation really depends on your program. It's quadratic in the size of the program you're simulating, and it's linear in space of the program you're simulating. Okay, this is a very technical thing that we just covered. Oh, we still have some 6 minutes. And this is an exercise that does not go into your exercise worksheet, or maybe it should. It's not an easy exercise. What you have to do, what if my universal Turing machine had 2 tapes instead of 1? What if I simulate everything in 2 tapes? And the dilemma is that there is a universal 2-tape Turing machine U, which simulates T steps of a 1-tape Turing machine, but now you do not have a quadratic blow-up anymore. So if the input length is V of n, the n is the input length of mu, then it will be linear, U times, not U². Here we had U², so it will be U times n plus t, where n is the size of the input and t is the number of steps you're simulating. And the space will stay the same. So if you use 2 tapes for simulating instead of the tracks that we're doing, you do not have to do the shifting. That's the whole point. So if you have 2 tapes, you do not have to shift anything. Like for example, let's look at this one. Here, when you're erasing zeros here, you're creating gaps, right? But if you have two tapes, you can just copy 0 on second tape, do nothing on other 0, do nothing another 0, copy 1 and 1 and 0 and just copy hashtag. So you do not have to, you just can directly copy to the second tape without shifting anything. We saw this in other examples that you can get rid of shifting when you have two tapes, and this is what is happening here, and you can do it in linear time. Okay, so this actually brings us to a very important topic. Again, we proved this, we're going to use this theorem. We're going to use this as anything I have, I can simulate in quadratic time. But now it actually brings us to time and space constructible functions. The motto today of time and space constructible functions is that imagine you have a kitchen timer. That means so you're baking a cake in the oven and you have a kitchen timer, and somehow your cake is half baked already, and it only takes, like, let's say 5 minutes for your cake to bake. It's completely useless to have a kitchen timer that takes more than 5 minutes to set up, right? So if you want to time something for 5 minutes, but it takes more than 5 minutes to time it, to set the kitchen timer, it's useless. This is the motto. So setting a kitchen timer for 3 minutes should not take more than 3 minutes. The same exact thing is it's not exact, so this intuition can be extended to time constructible and space constructible functions. Some of the bounds for time and space make no sense because they're not computable in the time they're bounding the Turing machine. So here is the definition. Let's say I have two functions, s and t, for natural numbers to natural numbers, and I want to use them as bounds for Turing machines. A time constructible function t is called time constructible if there exists a tn time bounded Turing machine M such that for all n, machine M started with a unary representation of 1n's, or just any input of size n, outputs the binary representation of tn and holds. So let me give you, let's give a more... So let's say I have function t that goes from n0 to n0. So it's a natural number. And let's say I will say that t is time constructible, that there must exist a machine M which in time OTN, so in asymptotically basically the same time as the function Tn. So it's asymptotically, it doesn't take more time than t. So it doesn't take more than 3 minutes to set up the timer for 3 minutes, basically. So M is OTN time bounded. So it basically works in time c time, doesn't make more than c times tn steps for some c. It's like this, so that when I start my machine on input of length n, and this input, for simplicity, we just take n many ones. So in this case, n is what? 1, 2, 3, 4, 5, 6, 7. So I start with n many ones. It should work in time c times tn, and it must output the result of tn. So the output will be some binary representation, let's say 0, 1, 1, 1, 0, such that this output, let's call this guy, I don't know, W, such that this W is actually t of 7 in our case. Okay, so basically it computes this function in binary. It starts with, as an input, it takes unary, meaning a length n. So it kind of knows the input is, in our case, 7. It takes this input and it computes your function, but it doesn't take more time than the function itself. So imagine what it means for a function to be not time constructible. That means this function, to actually compute this function, takes longer. So computing this function takes somehow longer than this function itself somehow. So it completely useless then to use this function as a time bound, because you might say that Tn is not time constructible and your machine is OTN bounded. You can never count up to Tn in time Tn somehow. So it makes no sense. So it's like setting a kitchen timer for 3 minutes takes longer than 3 minutes. It's like the same motto. So are there any questions on this before we go on a break? TN-ზე მეტი დრო გადის. ანუ TN ფუნქცია, so computing, so in a simplified version, forgetting the big O notation, you can say computing the function Tn takes longer than Tn. So for example, computing the value T14 takes longer than T14. T14 is a number, right? Maybe 237, I don't know. So T14 is a number, so it takes more steps than T14 to compute T14. Okay, let's continue. So time constructible and space constructible. Well, yeah. Space constructible is exactly the same. You start with an input of length n, so you take your n as bunch of ones. It can be any input of length n, but let's take bunch of ones. And you want to compute s of n. And we just have to specify how much space this takes. So we take, let's say in binary, you compute this function s of n. And if it doesn't take more than Sn space, then you say that your function is space constructible. So basically, space constructible function is a function whose computation doesn't take more than, so Sn is space constructible if your computation doesn't take more than Sn space. But again, there's a big O thrown in there because of this reductions and all the stuff that we know. So can you think of a function? There's some obvious, let me just make it disappear. So there are some obvious functions that will not be time constructible. Let's look at an example one more time. So what is a time constructible, right? It means you take an input, bunch of ones of length n, and you have to compute me t of n. And it should not take more than O(t of n) steps. Yeah, by the way, think of it what it means. I think I said it, but just once again, what it means that a function is not time constructible. Function is not time or space, let's say space. The function is not space constructible. It means that the computation of this function takes more space that this function specifies somehow. So it makes it's not your first, so if your machine is Sn space bounded, your first problem is actually computing Sn itself rather than looking how much space your Turing machine is taking up, because computing Sn itself requires more space than your Turing machine, whatever program your Turing machine is working on. So it's like your kitchen timer is more of a problem than the cake you're baking. If it takes longer to set up your kitchen timer than to bake your cake, and you're only concerned with time, then your kitchen timer is more of a problem than your cake. So this is what it means. This is why it's much easier to deal with, and we want to basically deal with time constructible and space constructible functions. But let's go back to my question now. So my question is, can you give me an obvious function that will take more time to compute than the function itself? There are some obvious candidates. We do not know that those things exist. Oh yeah, you mean uncomputable functions completely. Those are actually true, that is true. If the function is not computable at all, then of course it's not time constructible, because there does not exist a Turing machine that computes it. Of course, there does not exist a Turing machine that computes it in OTN time. So if your function is uncomputable, like a halting problem or something like that, then it will not be time constructible. What about something else? Look, here's the hint. Your machine has to read the whole input, right? To know that it's working with n, the input, it has to read the whole input. Do you know the function which, even if I read the whole input, I'm already over that function somehow, asymptotic? Oh, for example, what? Exactly. So if you take function log of n, as soon as you read the whole input, you already made n steps. So you're bigger than log n. So log n will not be time constructible. But not because some theoretical and hard reasons, just because we forced our Turing machines to read the whole input, and as soon as it discovers that it has to compute log n, and then it reads n, it already made more steps than log n. So log n will be not time constructible. Also other things like log n will also be not time constructible. So everything that is asymptotically slower than n will not be time constructible. So those functions that are asymptotically slower than n will not be time constructible. Here is cannot read the whole input log of n. The same for space, right? If you read the input of size n, you already took more space than log of n. You read n, you took more space, so it will also not be space constructible. Then the one is non-computable functions. You said if you cannot compute it at all, you cannot compute it in t and time also. But there are also other things. They are decidable, meaning computable nicely, but non-time constructible functions. And I will give you an example after I give you a time hierarchy theorem, because it uses that. But lemma number one, that the identity function is time and space constructible by two-tape Turing machine. That means, so the identity function is Tn equals n. You can compute this function in space n and time, in space on and time on on the two-tape Turing machine. So how would I compute this function, by the way? So let's look what I'm asking you to do. So I will give you my input is like this, and you have to produce an output. So if this is n, you have to produce n in binary. And you should not take more than n time. Can you give me the program to turn unary input into binary input on two tapes, not making more than a linear amount of time, not taking more than linear amount of time? ხო, ოღონდ რამდენი ერთიანი წერე იმაზე მეტი ნაბიჯი ასიმპტოტურად არ უნდა გადადგას. არა, ნახე, თუ წერე, so for example, if it has 4 ones, it should write 100. If it has 8 ones, it should write 1000. So I mean, the thing it has to transform unary into binary, basically. And I'm giving you 2 tapes to do this, and I want you to do it in linear time. So how would you do it? So let's say, so you start here, you read 1. So this is on tape 1. So you're on tape 1, like this. So what you do on tape 2? Actually, yeah, your answer is correct. It's a binary incrementer, and the whole point here is that you can analyze, and I'll show you that it works in linear time. So you do this in rounds. In round 0, so exactly as you said. So in round 0, tape 2 is just 0. In round bigger than 0, if head 1 doesn't read blank, so it's reading ones, tape 2 becomes tape 2 plus 1, the one you said. And then you move head 1 to the right. So increment, move right, increment, move right, increment, move right, increment, move right, until you see blank, and then you stop, right? But now, the whole point is that this binary incrementer has to go back and forth. Is it making more than ON steps? And I'm claiming that it's true, that it is making ON steps. So the question is the following. In how many rounds is only one cell visited? Let's look at only tape 2. Now look at the tape 1. In how many rounds, let's say I made n additions. So I did n increments. In how many out of this n, only one cell is changed? algoritme bisima şu konudaki. Oh, exactly. So we had this problem in our ADS or whatever. So in half of the time, only one cell will be visited. In a fourth of the time, two cells will be visited. And in general, in log n times, so what is it? This is n divided by 2 to the power something. So it's n divided by 2 to the power whatever the number is written here. So it's n divided by 2 squared. Then in 3 cells will be visited n divided by 2 to the power 3 times. So n divided by 8, right? So 3 cells will be visited every 8th time. 4 cells will be visited every 16th time. So this 8 and 16 are 2 to the power this, whatever the number is here. Only 2 cells are visited, n divided by 2 to the power 2. So what is the length of the thing? If I'm adding, I did do n increments, what is the final length of the binary string? So if I do n increments, what is the length of the final binary string? It's log of n, rounded up. So I only have to do it log of n times. So I go only log n cells are visited in n divided by 2 to the power log n times log n. Oh, why did this log n come here? So this log n should n divided by 2 to the power log n, like this. Yeah, times. Yeah, where does this n come from? Should it be? So this log n should not be here. This is just a mistake. It's n divided by 2 to the power log n. And I just have to add all of them. So I know how, so I have to add all of this, and this is the number of cells visited. Yeah, we had this in ADS, exactly this that I recall. So if you add all this up, this is a sum. I goes to log n times I divided 2 to the power I, and I goes from 1 to n, right? Yeah, this is the last summand, that's why I put log n here. So how many rounds? There are I many rounds where you visit, so they're this way, there are I many rounds, and then exactly as we did in the ADS, we do, instead of going from 1 to log n, we go 1 to infinity, it's smaller, and then you can factor out n, so you get n 1 to infinity I to I, and this is just a convergent series, this is some number, so you get On. Alright? So this proves that you can do it in On time, and by the way, as a corollary, we get that the functions n to the power k, 2 to the power n log n are time and space constructible. How do you do this? You compute binary n, as in lemma 13, just do the increment, and then you binary arithmetic. So if you want to n squared, then you first compute n in binary and then square it in binary. And it will not take more than square amount of time to square something in binary. And it's same with all the other things. So we do have some time constructible functions, the obvious ones. Hopefully these are where like n and log n and 2 to the power n to the power k and so on. And now we come to a very, very important theorem, is a time hierarchy. This is a crucial diagonalization argument, and I will try to show you how this works, and I advise you to pay attention. The time hierarchy theorem is actually what comes next. It is this, but it completely uses what we are going to prove now. So let me tell you the time hierarchy theorem first, and then I will prove the lemma 15, which implies time hierarchy. What does time hierarchy tell you? That you can do more in more time. This is not obvious at all. What I'm claiming is this. Let's say I have Tn, a function of n, which is time constructible. And let's say it's time constructible on a 3-tape Turing machine. That means there exists a 3-tape Turing machine that computes Tn in less time than Tn. So Tn is a time constructible on 3 tapes. And I'm also saying that t squared of n is OTN. Let me write what this means. So what does this mean? T squared n is small OTN. By the rules of calculus, this means that if you do this, and if you take the limit as n goes to infinity, this goes to, oops, it's not writing anymore or what? This, it's not working, the pen is not working. Let's write mouse. This goes to 0. So this is what it means. That really means that big Tn is larger asymptotically than the square root of small tn. For example, this could be, let's take an example. Let's use another program. Oops. My stylus died, that's what's happened. So I'll try to use my mouse to draw here. So let's take big Tn. Let's take it n cubed, let's say. So it's a function n cubed, and then small tn, let's take it as n. Then tn squared, t squared n or tn squared, is what? N squared. And then t squared n divided by big Tn, this is what? This is n squared divided by n cubed, right? Which is, oh, I can use my finger, which is 1 divided by n, and this goes to 0. Okay, so if I take n cubed and n, for example, Tn, so if I take asymptotically large time, which is larger than the square of the smaller time, so I have less time and more time. What time hierarchy is claiming is that whatever you can compute in Tn time on any tape Turing machine is actually less than whatever you can compute in big Tn time. What is the crucial point here? Let me show you the crucial. კვადრატულზე უფრო მეტი, საკმაოდ მეტი დროა. I think of a Tn as n cubed and think of Tn as small n. So whatever, so in terms of the example, this would say that whatever you can do, your algorithms you can solve in linear time are really less than algorithms that can be solved in cubic time. And the whole gist, the whole point of this thing is this here. You see? This crossed out line here. This crossed out line says that it is not equal. Of course, you knew that if you have an algorithm that works in linear time, of course, if it doesn't make more than linear steps, of course, it doesn't make more than n cubed steps. You knew that this was included here. But did you know that there is something here that is not here? This is what this is claiming, that they're not equal. That means there exists a language that can be solved or a problem that can be solved algorithmically in a cubic time, but you can never solve it in linear time. This is what time hierarchy is claiming. More time is better, really better. That means there are some problems in this computational world that are just physically not solvable in linear time. This is what time hierarchy is claiming. All right, this is why it's so important. So this is actually this is called like telling apart the complexity classes. This is a complexity class. That means this consists of all languages that can be solved in Tn time. So the complexity of these languages is Tn. This is the languages that can be solved in small Tn time. And I'm telling you that if this is the case, that t squared n is smaller than big Tn, then this complexity class is really different from the complexity class. There are languages that can never be solved in small Tn time. So there exist languages that can be solved, meaning problems or algorithms that work in cubic time, but you can never even theoretically think of anything to solve the same problem in linear time. So this is time hierarchy theorem, and a similar thing is true for space. There are some things that can be solved in more space, but not in less space. And in order to prove this, we proved the following lemma. This was by Hartmann and Stearns in 1965, which actually created complexity theory, this theorem that, these things are really different. And actually there was, in the 60s, there was really a blow up of such things. So people thought, there are so many things we can prove, and then they came to P equals NP and everything got stuck. But somehow some things are easy to prove, and some things, the similar looking things in complexity theory, are extremely hard to prove or impossible. So what are my assumptions for this lemma that will prove the lemma on time hierarchy? So you can see that this already exhibits. So let's say I take a function t prime n, which is bigger than n. So I take this function, bigger or equal to n, and I know that big Tn is really larger than t prime n, meaning if I divide this by this, it goes to 0. So think about n and n cubed again, or n, even n squared. And I make an additional assumption that this big Tn is time constructible on 3 tapes. That means there exists a 3-tape Turing machine that computes Tn in less time than OTN. Then what I'm claiming is whatever I compute in t prime n time on 1 tape is really less than what I can compute on 3 tapes in big Tn time. So let's read it differently. This says that there exists a language that I can compute or decide this language, so say if the problem is solvable or not, on 3-tape Turing machine in Tn time, but that can never be solved on 1 tape in small Tn time. And this will imply the general theorem. So what I have to do is now, what I have to do to prove this to you, is I have to construct a language which is decided by a 3-tape Turing machine in Tn time, and I have to prove that this language is never decided by 1-tape Turing machine in T small n time. And I don't have my phone, so if time is up, we have a lot of time, so we can actually prove it. So I'm constructing this language now. Instead of constructing a language that is accepted by a 3-tape Turing machine in Tn time, I will construct a Turing machine, and that language will be the language that this Turing machine accepts. Right? So I'm constructing a Turing machine now. So I'm constructing a 3-tape Turing machine M. So to construct a 3-tape Turing machine, I have to tell you what it does on an input. It starts with an input U hashtag V. So it starts with an input, so some string, some other string with hashtag in the middle, and let's say this input has length n. So what it does, first of all, it computes this function Tn. This function Tn is given in binary on tape 3. Well, function Tn is time constructible, so you can compute it in less time than OTN. So I compute the function Tn on tape 3, and I just write U hashtag V on tape 1. So I do UUV on tape 1, and I compute Tn on tape 3. Now, I have 2 tapes, so I have 3 tapes, right? Tape 1, tape 2 is empty, tape 1 has UUV, and tape 3 has Tn computed. So on tapes 1 and 2 now, I behave like a universal 2-tape Turing machine. So I simulate, what do I simulate? So I behave like a universal 2-tape Turing machine with input UUV. What this means, I simulate a 1-tape Turing machine MU on input UV. So I'm simulating MU on input UV, and I do this simulation for Tn steps of U. I have Tn written on tape 3, so I can do the simulation for Tn steps of U. If the simulation succeeds in time-bound Tn and MU accepts, then I reject. If this rejects, otherwise I accept. Let me pause this and explain. So yeah. So again, so if MU accepts within time Tn, within steps Tn, I reject. The otherwise being that MU rejects or MU exceeds the time-bound Tn, I will accept. So first of all, m will count tn steps in time OTN, right? This is exactly how by the argument of lemma 13. So 13 was the lemma of incrementing, so I do decrementing. So I have tn written on my, as I said, on tape 3. So every time my simulations makes a step, I decrement. So it doesn't take more than tn times. So incrementing n doesn't take more than n time. Decrement, that means that decrementing n also doesn't take more than n time. And so decrementing tn doesn't take more than tn time. So m counts tn steps in OTN time, so by algorithm level 13. So what this means that whatever this language accepts, whatever this machine accepts, L of m, is time, it's a 3-tape machine, so it takes less than tn time, OTN time, so it's inside time 3tn. So whatever the language that is decided or accepted, which is the same, by this Turing machine, called this language LM, is done on 3 tapes in tn time. So I have a language which is accepted on 3 tapes in tn time. Now I'm going to prove to you that this language cannot be accepted on 1 tape in smaller than tn time. How do I prove this? I assume the contrary. I assume that LM, the same language here, let me get the laser pointer at least so we see. So I assume the contrary. I assume that LM is accepted by some 1-tape Turing machine here, which works in less time. So let's assume. That means that there exists a 1-tape Turing machine, let's call this guy MU, right? There exists a 1-tape Turing machine MU such that language accepted by MU is the same as this language here. So LM equals LMU. Now, what I do is this trick. So I consider inputs of the form U hashtag V again, such that U hashtag V is length N. By lemma 12, which was that the simulation of a 2-tape Turing machine, the guy that I'm using here, takes linear time. So by lemma 12, simulation of MU with this input takes what time? Let me just open this up and make it larger. I know it's hard, but try to follow. So simulation of MU takes, this is just lemma 12, that simulation of T prime n steps takes, the length of the input is n, it takes U times n plus Tn, right? This is lemma 12. Let me just show you lemma 12. It's this. The lemma 12, there exists a universal 2-tape Turing machine. We didn't prove it, we left it as an exercise, which simulates T steps in O times O U times n plus T. So if the length of the input is n and you're simulating T steps, it takes whatever the length of the code of your machine is that you're simulating, U times n plus T. So I'm just rewriting this. But instead, I know that my machine works in T prime n time, so I'm simulating T prime n steps, so it takes O U times n plus T prime n, and by the definition of big O notation, this means that this is less than some constant times U times 2 times Tn, because T prime n, because T prime n is bigger than n, remember? T prime n is bigger than n, so I can substitute T prime n here, so I will get U times 2 times T prime n, and there's definition of big O, that means there exists C. So by definition of big O, when n is bigger than some n0, this is less than C times this. Okay? Now remember what my Turing machine was doing, right? It was simulating these steps, and it was counting if it exceeds T big N or not. So if this simulation here, which is bounded up by this number here, if this simulation is less than T big N, the simulation will succeed. So if this is less than Tn, I will not, so remember what I did? It does this for Tn steps of U. So I'm doing the simulation only up to Tn steps, and I want to see when this simulation succeeds within Tn steps. This will happen if this is less than Tn. Now let's divide both sides by T big N. So you will get T prime n divided by big Tn is less than 1 divided by 2C times U. Just rearrange the terms here. But now I know that this goes to 0. This is an assumption. This is like n cubed, this is like n. So this goes to 0. So this always holds after some n. So this always holds when n is bigger than some n1, because t prime n is OTN. So what, you might ask? I think actually we're finished. Why are we finished? Now I know that this holds when n is bigger than n0, and this holds when n is bigger than n1. So I take n bigger than n0 and n1. So I take the input of the size which is bigger than n0 and also bigger than n1. Then u hashtag v belongs to the language accepted by my one-tape Turing machine mu, if and only if this, by definition, mu started with input u and v accepts. Now mu started with input u and v accepts how I designed my machine, that if the simulation succeeds, then I reject. So this means that m started with uv will reject. This is the definition of my m, if and only if. And if this rejects, that means that u hashtag v is not in LM. So I just proved to you that there is some input which is in LM and not in LMU and not in LM. So LM cannot be equal to LMU. That means you can never create a machine that accepts this language here in t prime n time, less time than tn, on one tape. So this proves the lemma. And I will just tell you, and I will finish with this. Oh, should I do this as well? Yeah, might as well for... What time is it? Let's look at it again. Oops, yeah. Let's do this, and I will leave the space hierarchy theorem as an exercise. However, this will come in the exams, the space hierarchy. But let's. This is actually now. If I have this thing established, by the way, it's actually very easy to prove the actual hierarchy theorem. So let's say I know this. Let's say I know that if t prime n is OTN and Tn is time constructable on 3 tapes, I know this, the one I proved right now. How do I prove time hierarchy theorem? Now I want to show you that time Tn is inside time big Tn without any tapes here and things like this. Now, first of all, I know that what is time Tn? These are languages that are accepted by some tape Turing machine in Tn time. Well, if it's accepted by k-tape Turing machine in Tn time, I already know that it is accepted by one tape Turing machine in t squared of n time. I know this from when I simulate k-tapes on one tape, I get a quadratic blow-up. So I can go to one tape and write square here, right? This is lemma 4 is the simulation lemma. So I go time 1 t squared n. Now I know that t squared n is OTN. So now I can use my lemma here. Here I have t squared n and I know it's OTN. So I know that time 1 t squared n, using this, is inside and not equal to time 3 tape Tn. And of course, 3 tape Tn is inside time Tn. So time small tn is inside time big Tn, which proves the time hierarchy theorem, but the crucial point was number 2 here, which we used this one. Let me pause and at least you can let me... Yeah, begin is a mistake here. It's supposed to be small n. So let's get the pen and so this is supposed to be small n here, not big N. And once actually you have a time hierarchy theorem, might as well just push you even more further. Here I created a construction of a function which is computable. Why did this disappear? A function that is computable but not... What is happening? So let's look at it this way. So a function that is computable but not time constructable. What the hell? Okay. How do I do this? Right? Actually, it's very good for you to also look at it. But let me describe an example of a function. What? This new laser pointer, this new PowerPoint is not working for me. So by time hierarchy theorem, so time hierarchy tells you that if you really have a more time, that means quadratic and more time, there are languages here that are not here. So by time hierarchy theorem, there must exist a language that is in time 2 to the power n squared, but not in time 2 to the power n. Right? Because 2 to the power n squared is more than squared bigger than this one. So by time hierarchy, there exists something that is in time 2 to the power n squared, but not in time 2 to the power n, because if you divide this by this, it goes to 0. So there is some language that can be decided in time 2 to the power n squared, but cannot be decided by 2 to the power n. Okay, this language exists, we know by time hierarchy. So without loss of generality, I can assume that this language is a bunch of strings. If it's not, I can change it into a bunch of strings. So I change it into, so this is just strings. Now, chi-L is computable. Chi-L is, what is chi-L? Chi-L is a characteristic function, which is 1 when the string is in this language L, and 0 when the string is not in the language L. So chi-L is computable. That means that L is decidable. So chi-L being computable means that you can always tell me if string is in L or not. So chi-L being computable means that L is decidable, and L is decidable because it's decidable in time 2 to the power n squared. So chi-L is computable. So how do I interpret chi-L? Instead, I interpret chi-L. Chi-L is what? It takes inputs strings and produces 0 and 1 if string is in L, and 0 if it's not. Instead, what I do, I interpret as a function from natural numbers to natural numbers. How? This, I call it chi-L hat. Chi-L hat on number 5, let's say, is I write 5 in binary, right? And then I check if it's in L or not. So I can interpret this characteristic function as function from natural numbers to natural numbers. How? Let's say what is the value on number 17? I write 17 in binary and I check if it's in L or not. I return 1 or 0. Basically, if it's in L or not. So chi-L is now a function from natural numbers, natural function. And now this is the trick. I define a function fn, which is 2n plus chi-L of n. So f of 15 will be 30 plus, I write 15 in binary and check if it's L or not. So first claim, this function is always less than 2n plus 1, right? Because chi-L can only be 0 or 1, so it's always 2n less than 2n plus 1. So this function is on. Even though it's really hard to tell when this thing is 0 or so telling whether this thing is 0 or 1 actually decides L. However, it's always less than 2n plus 1 because it's at most 1. So you get this function is on. So I assume fn is time constructible. If it's time constructible, basically it should be computed in on. That's what's it, but not really. So I assume fn is time constructible. Then it is computable in on starting with unary input. Right? I advise you to think about why. So if fn is time constructible, then it is computable in on starting with unary input. Now, so think about this sentence. I will not explain why, because there's some 2 to the power logs involved and the binary changes involved here, and you can think about it later. But let's trust me on this one. I basically gave you an answer because of the binary thing, but whatever. So we can tell if fn is odd or even in on time, obviously. Because if you have a value of fn, which is a function in on, you can in linear time tell if the value is even or odd. So you can do this obviously, but as soon as you know that fn is odd, you know that chi-L was 1. And if you know that fn is even, you know that chi-L is 0. So in linear time, basically, in on time, you could decide whether chi-L is 1 or chi-L is 0 in on time. But now, given a string in B star, you can compute this string in unary in 2 to the power n times, which is obviously possible, and I advise you to think about why. and compute chi-L hat of the unary again, and this will decide your language L in 2 to the power n time, which contradicts the hierarchy theorem. I advise you to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to look at these 12 lines and think about them. I'm not going to explain this unary and binary thing. This all comes down to that the binary number. So when you go from what is the length of the binary number, you take log. And if you have a binary number, what is its length in unary, you take 2 to the power that. So this is where this 2 to the power comes from here. And also some things here. But yeah, just look at this thing. I wrote this and it's uploaded there. And it actually creates a time constructible function, which is decidable but not time constructible. So these things kind of exist. And by the way, there's also without a proof, we give that there is, again, Henny and Stearns in 1960 proved something like time Tn is inside time 2 Tn log Tn. And you can use this, we give it without the proof, that what does this say, right? Whatever can be constructed on k tapes in Tn time can be constructed on 2 tapes in Tn log Tn time. So instead of, if you put 1 tape here, we had square, like this one. But instead, if you use 2 tapes for simulating, you can get away with Tn log Tn time. And you can actually use this to conclude the tighter hierarchy theorem, meaning that this condition here can be made tighter. So in time hierarchy theorem, I require that the square of small tn is less than big Tn, but instead you can require not the square but the Tn log Tn to be O of Tn and conclude the hierarchy theorem. This is in the exercises and you can do this. It's easy, but somehow students struggle. And this I'm going to skip. There is a space hierarchy theorem. I'm just gonna the proof is very much the same in spirit as for the time hierarchy theorem. The space hierarchy theorem. First, you prove the lemma that if Sn is bigger than n and it grows asymptotically slower than big Sn, then whatever can be done on 1 tape in space Sn, whatever can be done on 3 tapes in space big Sn cannot be done on 1 tape in space Sn. And this, of course, implies the same exact way, the space hierarchy, that if big Sn grows faster than small Sn, then whatever can be done in space small Sn, whatever can be done in space big Sn is really more than whatever can be done in small space. So there are some problems, some algorithms that can be solved in some space and you can never reduce the space asymptotically. But by the way, this doesn't work if your things are not space constructible and time constructible. If you remove this thing, then these theorems do not work anymore. But space hierarchy and time hierarchy are very important theorems. I leave it as an exercise. I'll put it as an exercise for you to actually go through this proof and understand the space hierarchy. I see that it was hard to understand it in following class. That's why I leave it as an exercise. Exercise number 1 is to understand this. Exercise number 2 is to understand this. And these things will go into an exam, yes. And next week, we only have 2 hours left, and we will hopefully get started with Kolmogorov complexity and actually try to finish Kolmogorov complexity also next week.